In this problem, we're given this composite shape and we're asked to do two different things. The first thing we're asked to do is figure out where the centroid in the y direction is. So what y bar is, how high is it from the x-axis? And then second, we are asked to figure out what the moment of inertia is about this x prime axis. Now, the x prime axis is going to be an axis that goes through whatever we find the distances for the centroid. So it goes through my centroid. There's a couple of clarifying points I want to make about this problem. The first, all my units given are in millimeters. Second, all the thicknesses that you see right here are the same. So all of these thicknesses are the same and they are 50 millimeters. Finally, that leads to this. This is a cutout. This middle rectangle right here is a cutout. So this is negative space. That means whatever we do, we need to subtract out that moment of inertia and subtract out the area for the centroid. So now what we want to do is we want to break up this composite shape into simple shapes. The way I'm going to do it is like this. I'm going to have a big rectangle and I'm going to draw it over to the side, but I want to show you the shapes. So I'm going to have this big rectangle, which is this entire shape. So I'm going to have this, and it has dimensions of 400 plus 50, so 450. And then 150 plus 150, so 300. Then I'm going to subtract out this center rectangle. And this center rectangle has a dimension of, what is this? Well, this entire distance is 300. We need to subtract out 50 over here, 50 over here. So it has a length of 300 minus 100, so 200. This is going to be 200. And then this height right here is going to be, well, we're told this is 400 from the bottom, so we need to subtract out this height, so that will be 350. So this is 350. I'm going to write it on the other side. And then finally, we're going to add in my triangle. And my triangle has a base of 300. And it has a height of 240. Okay, I'm going to write that on the other side too. All right, so now what I need to do is I need to make a table. I'm going to have, this is my segment 1, my segment 2, and my segment 3, so we know what I'm talking about. So I'm going to write my segments. On my segments, I am going to have my area. I am going to have a y bar, so the centroid of each of my individual segments, and then I'm going to have y bar times area. So here's 1, here's 2, and here's 3. Let me put some dividing lines in here. So what is the area of 1? This is a rectangle, so my area is going to be 450 times 300. Let's do that. And we get, this is 135,000. So this is 135,000. Okay, now the second one is also in rectangle, but we have to remember we're subtracting this out. So we're going to have to make this a minus. So this is going to be minus 350 times 200. And that gets me 70,000. And then finally, this triangle, the area of a triangle, is 1/2 the base times the height. The base is 300. The height is 240. So we're going to have 300 times 240. And we're going to divide that by 2. So we get 36,000. Okay. Now we need to find y bar, which is the individual centroid to each of these shapes from this x-axis. And that's important. We have to keep in mind that we have to add in whatever offset to make it from this x-axis. Okay, the first one's easy. The first one starts the x-axis, so we just go all the way to the center. The rectangle, the centroid is in the center. So this is going to be 450 divided by 2. 450 divided by 2 is going to be 225. And that is going to be my y bar. 225. That's going to be right here. Okay, now let's look at this smaller rectangle. Where is its y bar? Well, we're going to have to add in 50 to whatever we get, right? This distance right here is not in this shape. So we have to add in that offset of 50. This has a height of 350. Half of 350 is going to be 175. So we're going to have that 175 plus 50. And we're also going to get that this is equal to 225 millimeters. So that makes sense because this is the thickness is the same all around, so it's just a smaller rectangle that's centered on the bigger triangle. So their centroids are in the same spot. Okay, finally, let's figure out the triangle. The centroid of a triangle is going to be up 1/3 from this bigger side. So we're going to have that the centroid is going to be 1/3 times h. H is going to be 240. So it's going to be 1/3 times 240, which is 80. But we have to remember now that we have to add in this entire length. So we have to add in the 400. This is 400 to this point. Then another 50, so 450 plus the 80. So 450 plus 80 is 530. So this y bar is 530. The next step we do in the centroid is we're going to multiply y bar times a. So these two columns together, 135,000 times 225 we get 303 7 5 1 2 3 zeros. Okay, let's do the next row. Minus 70,000 times 225. We get minus 1575 and 4 zeros. A lot of times you might see this worked in scientific notation, especially when you're working with millimeters. I had decided not to, I guess. So we'll have 36,000 times 530, and this will be 1908 and 4 zeros. Okay, so we have the important columns are these two columns right here. We're going to need to sum these. So if we sum these, we just add the columns together. 135,000. Remember to subtract out the 70,000 and then add in the 36,000. And we get this is right here, 101,000. Okay, now take your time with this last column. The numbers are pretty big. So we'll have 303 75123 plus 1575 and then plus 1908 2, 3, 4. Okay, so this gets us 300, what is that? 33,705,000. So remember, if you watch my last video, I showed you what y bar was. Y bar is going to be equal to the sum of the individual segments times the area of the individual segments divided by the total area. This right here is my total area. This is the numerator, the individual segments times their areas. And this is going to be equal to 33705 123 divided by 101 1230. And this tells me that my centroid is 333 millimeters up from the x-axis. So this distance right here is going to be 333. So now that we know this, when we're looking for the moment of inertia, we have to take the moment of inertia at the point that's at a axis that's 333 millimeters above the regular x-axis. We have to keep that 333 in, we have to remember that number. Now with the moment of inertia, I'm going to write the equation right here. I'm going to use a lot of the parallel axis theorem, and I actually use another table. So the parallel axis theorem says the moment of inertia about any axis we want. So the x-axis that we're looking for, and I'm just going to call it x prime right here because we're going to be looking about the x prime axis. This is going to be equal to the moment of inertia about the center of mass, the centroid of the object, plus this distance dy squared. So that's going to be the distance in the how far our centroid is to this axis that we're looking for, and we're going to multiply it by the area. So this is going to be multiplied by A. So when we do our table, how I do this is I'm just going to add on to this table right here because we're still going to use our segments, but we're going to look for the moment of inertia. These are probably going to be pretty big numbers. So we're going to look for the moment of inertia. We're going to figure out what our dy value is. So dy squared. We have our area over here. And then we can do a dy squared A column. And our final column can be this ix prime. Now we're going to use the same, and then we're going to sum it down here. So we're going to use the same shapes that we had, just the simple shapes that we have. And what we want to do is we want to go to a table and we want to look up what the moment of inertia for these different shapes that we're looking for are. And the shapes that we get, we see that for a rectangle about the x-axis, the moment of inertia is given by this equation, 1/12 b times h, where b is this and h is this way. Then for a triangle, we're told that the moment of inertia is going to be equal to 136b, which is the width, times h, which is the height, and that's going to be cubed. So those are the equations we want to use, and this gets us our moment of inertia about the centroid. So then we're going to have to figure out, let's get the moment of inertia about all of our centroids first. So for segment 1, the moment of inertia is going to be 1/12 b, which is 300, times height, which is this, and it's 450, and that's cubed. So what is that? 1/12 times 300 times 450 cubed. It's a really big number. So we'll put this into scientific notation. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 2.278 times 10 to the 9. And the units are a bit odd. The units are going to be in millimeters to the 4th. All right, now let's do segment 2. Segment 2 is also a rectangle. We have to remember we're subtracting it out. So segment 2 is going to be equal to 1/12 times b, which is this 200, times the height, which is 350, cubed. So let's put that in. 1/12 times 200 times 350. Oops. 350 cubed is how many digits is this? This is 1, 2, 3, 4, 5, 6, 7, 8. So I actually want to be careful with this because I want to subtract out this whole quantity. So I don't want the negative sign on there just yet. The negative sign is going to be over here. So this is going to be 7.146 times 10 to the 8th. Okay. And then finally, the triangle is going to be 1/36 b, which is 300, times height, which is 240, and that's going to be cubed. So 1/36 times 300 times 240 cubed. And that looks like 8 again. 1, 2, 3, 4, 5, 6, 7, 8. So 1.152 times 10 to the 8th. Okay. So now I need to figure out the distance from each of these centroids to the centroid of the composite shape. So the centroid of this red is up to, well, we have that somewhere. We have it. It's 225. So the centroid of the red is 225. The centroid of my composite shape is 333. So if I draw this, the distance, if this is up to 25, and my centroid is right here at 333. I need to figure out what this distance right here is. That's my dy. So it's going to be 333 minus 225. It's the distance from the centroid to whatever axis we're trying to take the moment of inertia about. So this is going to be equal to 108 squared. And don't forget to square it. 11664. 11664. And let me get rid of this. So we're going to do the same thing with 2. And with 2, it's the same. Here's my y bar. It's 225. So it's going to be the same distance. It's going to be, again, that distance right here is going to be that 108. So 108 squared is going to be 11664. Now, finally, we need to figure out the triangle. So the triangle has a y bar that's 530 from the x-axis. So we have to figure out what the difference is. If this is 333, this right here is 530. So this distance right here is going to be 500, and this distance is going to be 530 minus 333. And it's going to be 197. We square it. So we get, this is 38809. Okay. So now we're going to take this column headings tell us what to do. We're going to take this column right here and we're going to multiply it by our area. And I definitely did not leave enough room. So let me fix this. All right, so I just made this table just a little bit longer because these are going to be some pretty big numbers. And I'm going to multiply the area times dy squared, 11664. And we're going to get this is 1.574 times 10 to the 9th. Okay, we can do the same thing with part 2. So we'll have 70,000 times 11664. And we're going to take care of that negative sign pretty soon. And this is going to be 1, 2, 3, 4, 5, 6, 7, 8. So 8.165 times 10 to the 8th. And then finally, we're going to multiply this last one, 38809 times 36,000. And this will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So this will also be 1.397 times 10 to the 9th. So this last column right here is all we're doing with these columns is we're taking every term in this equation. So if you know the equation for the parallel axis theorem, you can figure out what all your column headings are. So we're now adding up what we have for our moment of inertia. So we're going to have this 2.278 e to the 9th plus 1.574 e to the 9th. And we're going to get 3.852 times 10 to the 9th. Okay, and this one we're going to do 7.146 e to the 8th plus 8.165 e to the 8th. And now we're subtracting out this entire quantity. 10. So this one is actually 10 to the 9th. So we're going to have 1.5311 times 10 to the 9th. And then this last one, we're going to have 1.152 e to the 8th plus 1.397 e to the 9th. Divide it by 10 to the 8th just to check. So this one's also to the 9th. So we have 1.5122 times 10 to the 9th. So now we sum all of this, and that gets us our moment of inertia. So we're going to have 3.852 e to the ninth minus 1.5311 e to the ninth plus 1.5122 e to the ninth. We add it. We'll divide by 10 to the ninth. And we get our moment of inertia about this x prime axis is equal to 3.8331 times 10 to the ninth millimeters to the fourth. So this is the answer that we would be looking for. And this is the moment of inertia about this x prime axis. And this x prime axis goes through our centroid, which is 333 millimeters from the x-axis.